Hey everyone, today we're going to be doing CNNs or convolutional neural networks, and those are neural networks that can be used to classify or detect images. And that's about all that I know, so passing it on to Naveed.
Yeah, so just like the simple neural networks that we talked about previously, the idea was inspired from biological neural networks. Same thing goes for the CNNs. So the visual system that humans use is a lot similar to what other mammals use, and because we do experiments on animals without any legal hurdles, um, researchers have like a great depth of knowledge when it comes to the visual system, um, particularly particularly the visual cortex, which is responsible for vision. So the researchers, I think the experiment was done back in the 60s or 70s. I'm not sure, but um, they came up with some interesting findings, and then later on, those findings were used to kind of mimic the same phenomena in a artificial computer. So the idea is, when they looked inside the visual cortex, what they found is, when a human is looking at something, the way I see something or I recognize something is not that like when I look at something, I'm not doing I'm not kind of seeing the entire object at once. What my brain is accustomed to is it first tries to find patterns, low level features, edges, and stuff, and then it later on combines those uh, to make the entire object, and that's how I recognize it. So it's kind of the object is getting recognized in these layers.
So you're
The
not
lower
seeing
layer,
pictures.
yeah, the lower levels first look at the low level features, edges and boundaries and stuff, and then the higher level then combines those low level features to come up with something that is more complex, like an eye of a person or something like that. So cnn's is kind of doing the same thing in a computer. So what we'll be doing is, we'll take a picture. How could have we done this without CNNs? Without CNNs, we could have taken a picture. Let's say it's a 32 by 32 pixel image. We can just simply flatten the entire picture into one long vector and feed the pixels directly to a fully connected layer, a neural network that we saw earlier. Why is it called a fully connected? Because all the neurons have to be connected. Sorry, all the features have to be connected with each of the neurons. So like if I have one neuron in the first layer, these entire 32 times 32 pixels have to be connected to that, and then same goes for the rest of the neuron. That's why it's called fully connected. But if you try to do it that way, there are lots of difficulties that arise. First and foremost is, if you have an image which is of a higher resolution, let's say it's 1,000 by 1,000 pixel image, 1,000 squares is a lot of number of pixels, and if you try to feed that at once to a fully connected layer, you'll have to have weights for the entire 1,000 times 1,000 pixels, which just simply blows up the space. Lots of trainable parameters are there. That's one problem, but there are other problems associated with it as well. For instance, um, if I have a picture, let's say I'm trying to recognize if there's a cat inside this picture or not. Let's say the cat is sitting in the upper left corner. Let me share the screen. So let's say I have this image and I want to recognize if there's a cat inside this image, and let's say the cat appears at this part of the image. Here's the cat sitting. Now, if I try to, because this picture is nothing but pixel intensity values, and if I try to feed this entire picture at once to flatten them into a vector and feed it at the neural network, let's say this is the neural network, this gets flattened to one long vector, and then I'm feeding that to this neural network. The way this neural network would train is that it would recognize that it's a cat, but it will recognize it in a way when the cat is sitting at the upper left corner. So if I then try to change its spatial position inside this image, let's say now I have another picture where the cat appears at this region, which is the bottom right corner. This picture is going to be completely different to this fully connected layer, this neural network, for the simple reason that now um, the cat appears at this region, but we know that this is the same cat. Like nothing should change. This neural network should be labeling this also as a cat, but to this neural network this is entirely a different picture, because remember we are just simply passing in the pixel intensity values, and it doesn't know um, just from the raw pixel intensity values that a cat it's the same cat, but now is appearing here. So in other words, the image contains spatial information. Spatial means it's located in space, and we want this neural network to behave in a way where even if this cat is changing position inside this image, this should not impact the output of this neural network. It should, in other words, come up with a strategy where it kind of fetches the features of a cat from this image and remove the spatial information that is associated with it. In other words, it should fetch the cat out of it and classify only the cat and not the entire image. It shouldn't pay attention to the global positioning. The spatial information should be reduced to just the features of a cat. uh, it turns out that the simple neural network is not able to do that. So that's another problem with it, with a fully connected layer. Now, how does a CNN solve these issues? First, of the huge dimensional complexity that arises with the fully connected layer, and another one with this phenomena of when the place is changed, it is then difficult for it to recognize it. There's a special technical term for it. So this is called transna- translational invariance. So we want this algorithm to be translationally invariant, meaning if the place of the images inside this image changes, it should be invariant. The algorithm should be invariant to that. It shouldn't impact the decision of the algorithm. Okay, now what is a CNN like? What does it do, which tries to mitigate this thing? Now I can talk about. Let me actually introduce the CNN through a simple example that I have here, and then maybe it will make more sense to you if I didn't talk about its conceptual background. So, what is a CNN? Let's say we have an image here. Um, this is just a simple image, a 6 by 6 image, and these numbers that you see, these are pixel intensity values. If you try to plot this image using Python or MATLAB, you'll see that because these are pixel intensity values here are 10 and here they are 0. So this region appears to be white and this region appears to be darker because of the 0 pixels. Um, it's just how images are constructed. They are pixel intensity values varying between 0 and 255. 255 meaning fully bright, 0 means fully black. But just for simplicity, we know that half of this image is white and the rest of the half is black. This is clear, right?
Yep. Black on the left,
Yep.
black on the left, white on the right.
Yeah.
Or was it the
Yeah,
other way?
yeah, the other way around for me.
Oh,
So so what is a convolution phenomena? So in convolution, what we have is called a filter. So a filter is nothing but a smaller rectangular array of numbers. So here you see this rectangular array of numbers. Um, it's a 3 by 3 matrix. So we have just a simple matrix with 3 rows and 3 columns. How do we compute a convolution? Um, so just like I said, we need this filter and we have this image. And a convolution is a phenomenon that is um, that like we take this filter and we convolve it with this image. In other words, you can say we pass this image from this filter and it produces an output, and that's what is called a convolution. Now, how we compute this convolution, the mechanism is super simple. We just simply take this filter, this 3 by 3 rectangular matrix. It's not rectangular, it's a square matrix. We simply place it on top of the image, starting from the upper left corner. So we take this, place it on top of this green region that you see here. Um, and then we just simply do pointwise multiplication. So we take 1 multiplied with 10, take 0 multiplied with 10, take -1 multiplied with 10, and so on. We just simply take the number and pointwise multiply it with the image. And whatever the output is, we just simply add all of them together. And that single number is then the output, the first pixel in the output here that you see, this green one here. So if you try to work out this math, it will turn out that this becomes 0. And then we just simply shift it one place at a time. So we then shift it one place to the right, and then this entire filter is placed on top of this region, and again do the pointwise multiplication, and again do the addition, and that's how this 30 is generated. And then shift it once more, and that 30, and shift it once more, and that 0, and then we shift it one place down, and then do it for this region, and so on. And that's how this output is generated. Once you do that, you have performed a successful example of convolution. You have taken this image, taken this filter, you have performed the convolution, and this is what the output looks like. So the term convolution, it comes from signal processing. It's a phenomenon where you have a filter, and a filter is a name given to any circuitry where you have a signal coming to it, and the signal passes from that circuitry. It could be anything. It could be like an electrical circuit, and then um, it produces an output. So the way you generate an output for such a system is you make use of a phenomenon called convolution. And for 1D signals, it is computed in one way. For 2D signals, like an image here, we convolve it in the way we compute it in the way just like I described, by simply placing it on top of it and doing pointwise multiplication, addition, and so on. Is this mechanism clear to you?
Yep, but what does it help us with, like,
Yeah, I'll
after
talk
doing
about
all
that.
of
But
this?
but do you understand the way we compute a convolution?
Yep.
Like
Yeah.
that's so brilliant. Do you see? It's so cool.
Yeah.
Yeah.
Sure.
Farhan,
Now,
do you see what's happening in the, like, do you see what that middle matrix is doing?
yeah, yeah. Just take a guess. It's written here as well.
I
Just tell
mean,
me what is
what
going on.
I think is it's finding the tens and like putting them at the center of focus by the end of it.
Tens? What do you mean by tens?
But like where the pixels are more dense, it's gonna uh like it's gonna find where the pixels are most dense, and then make a matrix which are centered, which has the
Okay.
most dense centered. Yeah.
Victor, do you have any thoughts?
No, I don't have any thoughts about this, about what it's doing. I get the
But do you under,
transformation, but I don't know what like the transformation is doing.
but do you understand how to compute a convolution, right?
Yeah.
Perfect. Let's see what it is doing. So I gave it the name of a filter. What is this filter doing? And what is a filter in general? Just like I said, filter is something uh, that changes a signal that you pass from it. So suppose um, will be introducing some terminologies from signal processing. If you understand it, perfect. If you don't, that's also perfect. But there's a term called low pass filter. What does a low pass filter do? If you have a signal and you pass it from a low pass filter, what happens is at the output you get a signal where only the lower frequencies are passed and the upper frequencies are just simply blocked. That's what a low pass filter is doing. That is for 1D signals. In images, what is the role of a filter? So a filter can do lots of things. Different filters perform different jobs here. This filter that you see here with these respective numbers, this is a vertical edge detector filter. So what it does, once you convolve it with a picture or once you pass a picture from it, is that it is going to detect the vertical edges in your picture. So pay attention to this, to these smaller images that are here on the bottom. So this image is, the left side is completely white, the right side is dark. And if a white region is combined with a black region, you see there's an edge forming there. This is an edge, this red circle that you see here. And just like I said, this is a vertical edge detector. It looks like this, but you shouldn't be confused about what it looks like. Just forget about that. But look at what is it generating in the output. So in the output, what it is generating is the left side is darker, the right side is darker, and only the middle region is brighter or white. And what was in the middle? If you see here in the middle, there was a vertical edge. So in other words, it highlighted the vertical edge and it reduced or it darkened the rest of the picture. So if you take this filter and pass it from any image, here it's just a simple black and white strips of just these two strips. But if you take this and pass it from a real world image, what would happen is at the input you'll have the image, at the output that most of that image would be darkened, and wherever there are vertical edges, only those regions will be highlighted at the output. Does this make sense?
Yes, it does.
Perfect. So just like I said, this is called a vertical edge detector, and particularly it is detecting edges which are transitioning from white to black. If you try to take these negative signs from here and place it in here, so these become negative one, negative one, negative one, and those become positive one, positive one, and positive one. And then if you try to convolve that with an image, that would only detect edges which transition from black to white. So you can even detect places where the transition is happening from white to black or transition happening from black to white. So just by altering these numbers, you can detect different features inside an image. And if you try to rotate this filter by 90 degrees, in other words, you try to make this negative one appear on the top row and this positive 111 on the bottom row and these zeros on the middle, this would then automatically become a horizontal edge detector. So if you then take that filter and convolve it with any image, the output would be an image where only the horizontal images would be brighter and the rest of the image would go darker. So that would then become a horizontal edge detector, right?
Question. So,
Yep.
um, based on what I'm looking at here, it looks like the result of the convolution could could have negative numbers. But is there a step that's removing those negative numbers?
Could have negative numbers.
Um,
Okay, yeah.
yeah,
So what we do
if
is,
I would take the convolution, the filter right now, and then flip it horizontally, I would expect to have the negative of what we have. Is that possible?
so yeah, so here that could happen. That maybe if you put certain numbers here and you convolve it,
Yeah,
maybe at some places it could appear to be negative. Now, I don't know how signal processing people deal with it, but for us machine learning persons, we don't directly feed this to the next layer. We also apply the nonlinearity on it. So when you apply, let's say, the railway tuition function on it, it would block the negative numbers and just allow the positive numbers. So those would become zero, and the negative numbers would become zero, and the others would become positive. But even if they are, but even if there are negative numbers in it, that doesn't hurt us, right?
sure. Yeah,
Yeah, so even if you have those, it wouldn't hurt us. Remember, so this is just for explanation what the output looks like. Now, the $1 million question is, how do we come up with these filters? So we have explicitly here put these numbers here, and we know that this is a vertical edge detector. In other words, it is fetching edges from my image. Um, do we have to come up with these filters ourselves? Or can you tell me any other way of where we can where this could happen automatically?
Mm, mm.
I think that's where neural network excel. Like you mentioned last time, like they are really good
Exactly,
um, at creating
exactly.
features.
So that's the real thing here, that we don't have to design these filters. Just for explanation purpose, I told you it's a vertical edge detector. Maybe the neural network doesn't require vertical edges. Maybe it requires something that we don't even know of. So these numbers here, we treat them as the weights of the model. So we don't have to fix these things ourselves. Otherwise, you'll have to then come up with lots of filters with different features that you would have handcrafted. And you don't even know if those would be significant enough for a model to make decisions, to place their decisions on. So what we do is we make these as the weights of the model, and we let the process of gradient descent come up with whatever this neural network is needing in order to classify images. So if it needs a vertical edge detector, it can design that for itself during the training. If it needs a horizontal edge detector, it can does that. It can do that. But if it needs anything else that we don't even know of, whatever those numbers could be, it just comes up with those numbers using gradient descent, right?
Cool.
Great. So this is what a convolution is. And now let's talk about how do we. So you now know a convolution, what a convolution is. Before we can make use of a convolution, there are some other technical terms and phenomena that happen. Although this is the principal operation, that's literally what happens. The rest of it is just some other implementation details. So if you look at this image here, what is the input dimension of this image? It's a 6 by 6 image, right? And what is the output of this?
Four
So
by
this is
four.
it's a 4 by 4. So it's usually the name that is given to the output is called a feature map, because you are extracting features from your image. So it's an image, but it's, for technical terms, it's called a feature map. So one thing is, if you use one filter, you come up with this feature map. You can combine multiple filters to come up with multiple feature maps. So here we just have one filter. You can, let's say, take 10 such filters, and all of them are trainable. And each of the filters could come up with some interesting feature that is significant for doing image classification. All those 10 filters would be learning their own feature maps. One of it could be doing vertical edge detection, other could be doing horizontal edge detector, other could be doing circle detection, other could be doing maybe whatever. So you then have 10 feature maps in the output, and then you can feed those feature maps directly to your neural network to make decision, or you can even combine more such filters. So in the first layer, you have 10 filters. In the second layer, you can have 20 more filters. In the third layer, you can have some more filters. And remember, in the beginning, I told you that the visual cortex, the way it works is it first comes up with some low level features like edges and boundaries and stuff, and then in the subsequent layer it combines those to come up with larger structures. So you can combine multiple horizontal edges, multiple vertical and horizontal edges to come up with polygons or circles, and then those circles could be combined in certain ways to maybe come up with, let's say, the face of a cat, the eye of a cat, or the legs of a cat, or whatever. So those low level features are then subsequently combined in the subsequent filters, subsequent layers of the convolutional network, to even come up with some higher level features. And that way it is becoming more easier and easier for the neural network to then recognize what's inside that image, right? And another interesting phenomena that is happening here is, I told you this is a edge detector. So this is kind of a lens where you, once you pass your image through this lens, all the horizontal or all the vertical edges in your image becomes apparent, and the rest of the stuff just goes away. So one of the problem that I told you about was, suppose the cat was sitting in the upper left corner. How could then a neural network distinguish between that and another cat which is, let's say, appearing in the bottom right corner? Well, it turns out if you have these feature filters, this automatically fetches those information from the image. So it's kind of scanning the image for those features. So this one is scanning the image for vertical edges, and it doesn't matter where those vertical edges appear. It can scan it for it, and it can fetch that out for you. So it is kind of making this um, translational invariance phenomena, where now the position of the feature doesn't matter where they appear in the image. It can scan it for them and it can fetch those out for you, and then you can subsequently make use of them to come up with even something more complicated, and then finally classify them into one of the categories. Does this make sense?
Yeah.
Great. So this is literally the backbone of a CNN. But there are, just like I said, some other technical details that we have to take care of before we construct a complete convolutional neural network. So one of it is called padding. So why do we need padding? Just like I said, the input dimension of this image is a 6 by 6 image. The output now is a 4 by 4 image. So in other words, it is reducing the shape of this image. So like if you take this filter and place it on top of the upper left corner and then shift it one pixel at a time, you see that these middle pixels are appearing in lots of different so like in lots of different output pixels. So like if you pay attention to, let's say, this 10 here, this appears in the first round of convolution, then it, when you shift it, once you shift it by one, it appears then again and again, and 3 or 4 number of times it appears. But if you look at this corner pixel here, this 10, this just appears once, and then the filter is moved away from it. So in other words, these features or these pixels that appear on the edges of the image, they kind of get the least the least attention. So those kind of fade away in the output feature map. So in order to prevent it from doing this, in order to pay more attention to the edges as well, we can, before doing convolution, we can pad this image with zeros on all of the 4 sides. So we can just simply add zeros on all of the 4 sides so that these information that appears in the corners of this image doesn't fade away with convolution operation. Does that make sense?
Yep.
So that's padding. That's what we also do before we apply convolution on it. There's another term called stride. What is stride? So I told you that once you place this feature, this filter on top of this image, you compute this one output pixel, and then you shift it at once. So that shifting by once means the stride is 1. But sometimes you could want the stride to be 2 or 3. So once you place it here, you can shift it not just 1 pixel at a time, or 3 pixels at a time, or 4 pixels at a time. No one does it 4 pixels at a time. Usually stride is 2. But the function of stride is it shifts the filter not just 1 place at a time, or it shifts it 2 places at a time. Now the question is, why would we want to do that? Well, we want to do that if we even want to make this feature map even more smaller, because if you increase the stride, then the output dimension of this feature map would be reduced even further. And I'll write a formula which would tell you what would be the output dimension on the whiteboard. But the just for you to understand, stride just simply means how much you shift this filter while you compute the convolution to compute the 1 pixel at the output. Is that clear?
Mm-hmm.
Yes.
Yes. Yes.
Perfect. There's one last thing that I want to talk about, and then that would conclude the entire convolution phenomena, and then you can just simply combine multiple of them to come up with whatever CNN you'd like to. And that's called pooling. What is pooling? So let's say this image we have here, and we convolve it with this filter here. This is the output. Now at the output we have this feature map. Sometimes what we would like to do is to reduce this feature map, maybe because we have used too much filters and now the output space is just simply very huge, and maybe we would like to squeeze that um, by some amount so that we don't have lots of output features to take care of. So what we can do is call what is called pooling. So there are multiple ways to do pooling. One of most commonly used one is called max pooling. So what the max pooling does, let's say we have these 4 pixels in the feature map, 0, 30, 0, and 30. We can take these 4 pixels and replace it by the maximum pixel. So we can just simply take whatever is the maximum pixel in these 4 pixels here, and the output would be then just 1 pixel, which would be the maximum of these 4. And then we can shift that 1 at a time, and then take the maximum of these 4, and then one more and maximum of these 4, and then shift it 1 down and maximum of those for, and so on. And that would reduce the feature map even further. Now, when you do max pooling, of course, when you are squeezing or when you're taking the max of something, the rest of features you are dropping. In other words, you are dropping some information. Well, of course, you are dropping some information, but once you take the max of it, what it turns out is that it highlights even the output features even more. So suppose these 4 pixels at the output, it was like representing, let's say something important. These 4 pixels. If you take the max of it, that max of it just simply highlights that thing even more. So although you are dropping some of the pixels, but whatever comes out of the pooling, it would be just more intensified version of whatever feature you were looking for. So that's one explanation for it. But of course, this is just one explanation. Why does pooling make a convolutional network better? This is just one explanation for it. Of course, there could be some other phenomena which is not even explainable, but it was shown that if you apply pooling, you can reduce the output feature space, and it turns out that if you do that, it even further improves the performance of a CNN architecture. So once you perform convolution and followed by the pooling operation, that usually concludes one convolutional layer. And then you take that and then apply another convolution layer and another, and this just simply boils down to whatever you have been doing in the simple neural network, where you have one fully connected layer and then another and another and so on. So how many layers you want to use, a hyperparameter, how many filters you want to use, another hyperparameter, what should be the size of this filter, another hyperparameter, and so on. Do you want to do pairing or not? That's also something, that's a hyperparameter, you can experiment with it. So there are lots of things you can play around with it and then come up with whatever architecture of a CNN that you'd like to, and then see how it performs on your problem.
Hmm.
So we talked about what it
I have
mitigates.
a question about
Mhm.
pooling.
Go ahead.
You mentioned that the pooling comes after the convolutional layer. Would you
Hmm.
put would you do pooling if you had multiple convolutional layers? So in your CNN, you'll start with multiple one or several convolutional layers, and then you'll go on to fully connected layers. Would you normally put pooling after every convolutional layer?
Yeah. So pooling is applied after every convolution layer. So suppose in the first layer you applied a convolution layer where you had, let's say, 30 filters or 32 filters. Once you convolve your image with those 32 filters, you immediately follow it by the pooling layer. And then you take the output of that pooling, and maybe if you'd like to do another convolution layer, and you take that and apply another convolution on it, and then immediately follow it by a pooling layer. And then finally, you would like to maybe feed it to a fully connected layer. So you can then feed it to a fully connected layer. Does that make sense?
The output of so let's say you have 16 filters
Mm-hmm.
in the convolutional layer.
Mm-hmm.
Are those feature maps combined after that layer, or they stay separate?
They stay separate. So
Okay.
suppose you have this image here,
Yeah.
and let's say you apply a convolutional layer and you have 16
Mhm.
filters in it. Let's say
Yeah.
the initial image was whatever height times width. Once you convolve it with these 16 filters, the output would be whatever the feature map size would be. It would be reduced. The formula for it is n plus 2p minus f divided by s. Sn just simply is the input size. So usually the images that we feed to a neural network are square images. So I have written here h by w, but you can replace it with n by n. So that's the input shape. This p is here the padding. If you have done padding, then how much padding have you done? So if you have just padded one layer of zeros around this image, this p would be one. If it is two layers of zeros, then this would become 2. So this is the amount of padding you have done. This is the filter size. So if the filter size is a 3 by 3, it's a 3 by 3 filter, then this would be 3 here. And this S is the stride that you have. So the increasing the stride just simply reduces the output feature, the dimension of the feature map. But
Hmm.
but that's how you compute the dimension of the output feature map. Now, the question you asked was, if this is n by n pixel image and you convolve with 16 filters, what is going to be the output? Well, the output is going to be whatever the size of that filter is. Let's say we'll call it k. So it's a k by k feature map, and we would have 16 of them.
Yeah.
So 16 those feature maps. And if you would like to then apply another convolution layer, let's say um, with just one with just one filter. Now that filter would have 16 channels because you'll be applying it across all those 16 um, feature maps. So even though it's just one convolution filter, but it would have 16 layers. Does that make sense?
So correct me if I'm wrong, but if you would take like the same convolutional layer and then
Hmm.
you would add it again and again, the number of parameters would just increase exponentially, right?
Yeah, those would increase based on this thing.
Yeah.
And that's why sometimes, so that's why there were so many different things to reduce the output feature
Yeah.
space. So things like stride and things like the pooling layer. Sometimes you even do what is called global average pooling. So the global average pooling does is that it averages all those feature maps into just one k by k. So if you have 16 of them, you just take the average of the entire feature space and it reduces it to by k by k. Sometimes people also do that just to reduce the output space.
Yeah.
But compared to the input, but like if you compare it with the raw neural network, like the fully connected layer, if it was 1,000 by 1,000 pixel image, 1,000 square is a huge number. So now that is significantly reduced because now you just have these trainable parameters. It's just 3 by 3. Or if you would have fit this directly to a fully connected layer, it would be 16 times 16, sorry, 6 times 6, which is 36. So you then have 36 parameters to train. Here you just have 3 by 3, which is just 9 parameters. So as you can see, it reduces the trainable parameters. So the problem of having more trainable parameters is also reduced. Does that make sense?
Yes.
Yes.
So with that, I think I have covered every single aspect of what would be required in a convolutional neural network. The rest is just simply once you have finished the convolution operation, you take the feature map and you just simply flatten all the pixels in it and then apply what is called a fully connected layer. You can apply a fully connected layer, you can even skip that and directly feed them to the output layer. We just have to classify them. But even sometimes like a single or two fully connected layers would also further make the model more complicated and further recognize complicated images.
Right.
So yeah, so that's also part of it.
Yeah,
So I think Jen,
I have a question.
go ahead.
Uh, while we're performing pooling, we're actually taking the greatest value out of a chunk, right?
Yeah,
So what if the most of the chunk is like, for one case it's empty and then we have like 30, so it picked 30, and for the other case we had like 30 and a few more values, right? For both the output would be 30, right? So won't it be
yeah.
misleading?
It
Because
would be kind of losing some of the information, although
right,
it would not be misleading that much for the simple reason that if you have a chunk where there are other pixel intensity values and one of it is 30, the other ones would be just pixels with a slightly more darker regions. 31 would be the brightest of them. So whatever that region is representing, it would be even more highlighted just because of the fact that you are taking the maximum of it. So it's kind of
right.
highlighting it even further, not misleading. But of course, whenever you are squeezing something, you are dropping some of the information. But the cost of it is too much if you include them because of the dimensional complexity that arises with it.
Fair enough.
The way I'm thinking about it in my head is just that the your neural network wants to detect places where there are features that it's looking for, if that
Exactly.
makes sense,
That's exactly what's happening.
or sections where there are those features. Yeah. Okay. Well, looks like Naveed has lost power again. Is everyone else still here?
Yep.
That's fine. Because um, we were about to go on to the coding part anyways. So it's perfect timing. So I'll just pull that up. Yeah. It's funny because you never lose power, do you, Burhan?
We actually have solar installed, so even
Oh.
if it does, so it doesn't affect.
That's good. I'll just try and keep an eye in case he comes back. So let's see, where were we? Okay, so this is the course. This is a course overview and all of the great stuff we've done so far. So last week we were here, and today we're going to go on to a project where you can, train your own convolutional neural network. Ready?
Yep.
Cool. So this is the exercise. Super simple. I've given you a notebook where we're training a convolutional neural network from scratch, and this is a super classic data set that we're going to use, example. And then I've given you some more data sets which you can train your own model on, but we'll get to that later. Let's have a look at the code for a convolutional neural network. So do you see anything here in this first section that is new that you haven't seen before?
We got a bunch of image data generator, image to array, load image. Yeah, this chunk.
Right.
Yeah.
So within Keras, there's pre-processing submodule, they call it, and then within that there's these image functions.
Right.
These are just for like processing images. There's no this is not a deep learning thing here. This is all the pre-processing stuff, but useful.
Oh.
Anything else?
I don't
I
think
can
so.
see the max pooling
Yeah.
that you mentioned.
Yeah.
So the pooling, flattening, not sure what
Just this
conv2d
chunk.
does, but
Which
the
one?
max pooling I conv2d.
Oh yeah. Okay. Yeah, so we used this submodule before for the dense layer because that's the
Yeah.
normal fully connected layer in a neural network, which we did last time with the fundamental neural network. So we have now these three new types of layers. So if you remember what we did last time, we took the sequential model and then we filled it with dense layers. But now we just have more building blocks that we can apply to the same type of to the same type of model. So let's go on to the maybe I can Victor, maybe I can reduce. You have a little bit of background noise. Mute it when you're not talking.
Sorry about that.
That's fine. Let's see. Does that help? Yeah, that fixes. Just you can talk whenever you want. Just unmute it when you talk. So the data set here, unlike the past data sets, it's not going to be like tabular data, but it's just a zip file with folders of images. That's the whole data set. And then, of course, we need to have labels to train the network, to train the model. So here I can connect without GPU. That'll be fine. But so if we run this here, it's just starting up the notebook. What it's going to do is it's going to download that zip file from the internet. And if I run this one, then it will unzip the zip file, and then we'll see here what we're going to get. But so what we get and what we're processing here in the next chunk are these directories. So here I'm going to click refresh because it's just downloaded. We'll see it downloaded the zip file and then it's unzipped it. So this has been really nicely organized. for us, because it's exactly set up for this kind of training. We can ignore this this Python that we just need the images. And as you can see, we have training data set, validation data set, and each one has cats and dogs images in there. Now we can use any number of images that we want, and we can split it up however we want into training and validation data sets. But this is just a nice way that they've set it up. And so we just get those paths of those 4 directories. We get the list of files in each path. And if your directory structure is different for your data set, maybe it's like the other way around, where you have cats and dogs, and then in each one you have, or maybe you have cats, dogs, and another animal. Well, in that case, you can just use ChatGPT to figure out how to get this part exactly how you need it. So what this so right here, I think this code is actually just showing some of the images that we have in the data sets. You can see like there's a lot of cute cats and dogs in there. And when we create the model, when we train the model, what we're going to do is we are going to use this image data generator. I'll go back to the code we were just looking at, but here it's taking in those directories of images, and then it's resampling all those images to be in the size that we want them. Here's the target size of 150 by 150. It's really important, like if you followed the theory part of this, to realize from Naveed's explanation, let's just see, from Naveed's explanation, that if the input image is not of the size that's expected by the convolutional layer, that it's not going to work, right? Because all of those parameters that are set in the architecture, like the padding and the size of the filters and all of that, they're highly dependent on the size of the they're sensitive to the size of the image. So it's important that we do all of this pre-processing. Now I'm going to be honest, like I don't entirely know how this generator works, how the details of it works, but the idea is that it's just going through the whole directory, and it's processing the images in a way that can be passed on directly to the model.fit. If you have any problems with that when you're actually doing the assignment, just let me know and we'll work through how to get all the images in the right format, because that's normally the annoying part. Now let's go to now if everyone's good with that, let's go to the fun part, which is building the actual model. Sound good?
Yep.
Cool. So what are we looking at here? Similarly to last time, we're using the sequential model, and it just takes a list of layers and it builds a neural network sequentially out of those layers. We have a simple convolutional neural network here. We have one convolutional layer followed by max pooling. As Naveed mentioned, you normally use that after every layer. So if we would have multiple layers, I guess then it would be something like this, you know, and there it's even giving us more. So we have one convolutional layer, we have max pooling layer, and then we have a flatten. Does anyone want to take a guess what this flatten layer does? It's easier than you. It's really, yeah.
Probably because the images are like the colors are like 3 items, like RGB, probably, I'm not sure, and flattening them out to a single value or something.
Close, but basically what this does is, like, if you think about what comes out of the max pooling, as Naveed was saying, you're still getting feature maps, right? And the feature maps, they're like, they're rectangles, or yeah, they're rectangles, squares, whatever. But you cannot really pass a rectangle into a neural network, because the layers are just they're flat, right? So it's just taking the individual values of the matrix, and it's just putting them in one long vector. That's all it's doing. So if you have so here, for example, we have 512 neuron hidden layer, although this is 64.
64.
so I trust the code, not the comment here. So so here we have 64, and I guess that means that that what's coming out of max pooling. Let's have a look. Let's go back to the beginning and see. So we start with a convolutional layer, and that convolutional layer has 16 filters. Each filter is 3 by 3, and then this is the input. This is the type of the images that can come in. All right. So in that case, I might mess this up, but Naveed gave us this this formula before. Then we should come up with something like 16 different feature maps, and those feature maps should be we're assuming that the stride is going to be like 1, and I'm not sure about what the default padding would be, but we would end up with something like 16 feature maps, and each one should be so the max, each one should be something like 150 by 150, right? But then the max pooling should make that half. Okay.
We lost
So
Victor, by the way.
okay, they're just dropping like flies today. I'm gonna go check that math later. That's pretty interesting. But in the end, we end up with 64.
64 new.
Oh, you know what it is here? This 64 is the number of neurons in this layer, but the inputs going into it can be any number of inputs. Does that make sense?
Right.
So if we go down to there, he's back. Hey, Victor. We're just still counting the neurons in the network.
All right.
So what we end up with after the convolutional layer is something like, so we end up with 148. Okay, that makes sense because of the padding I was mentioning. So if there's no padding, we end up with 148 by 148 by 16, which is the number of convolutional layers. And then after we go through the max pooling, that halves that, right? That halves the size of the feature maps. So we end up with 74 by 74. And then we flatten that, and we end up with 70. Probably this is, let's see, this would probably be 74 times 74 times 16. If someone wants to check that, that should be something like 87,000. And then that 87,000, those 87,000, that 87,000 vector then gets passed to the neural network, and that gets all combined into one final output neuron. Did you follow that?
Yep.
Cool. It's definitely worth just kind of thinking that through yourself. Interestingly here, there's not too many parameters trainable parameters in the convolutional part, but there's a lot in the neural network itself. So let's run that. This is just setting up the model here, and the binary cross entropy part, Naveed can tell you a bit more about why it uses that as the loss function. But we've seen Atom before, right? Have we?
Yep.
Optimizer. Okay, we have. Cool. And this is the part where we're feeding those images in, and this is the training part. This doesn't take all that long, and to train, maybe, I don't know, 5 minutes or something. And the reason is basically that well, there's not too many epochs, I think, and then also there's not like all that many. There's not all too much happening in this model. So yeah, I will guess I won't be able to run it right now for you, but you can go run it on yourself. It just takes a few minutes. The generator here. So once it's trained, we can run it on the validation data. Now we already know from here that the validation accuracy is 0.69 because it does that when it's training. But here we see that again here, along with the loss, which we already knew. But we see that again here by running just model evaluate. Make sense?
Yep.
Okay. So then I thought, yeah, let's just take any image out there of a dog or a cat, and let's test the model out that we just trained, right? So I took here image of one of my favorite dogs from here at home, and I've passed it into the model, and the model has reliably determined that this is a cat. So there could be a few different things going on here, but what we see from the validation, I mean, and it's important to, try and throw it lots of different examples of images to see how it works. And
Right.
you see from the validation is that, it's we have 70% accuracy. So it makes sense that, okay, this is kind of a goofy image. We cannot be sure that it's gonna be properly classified. And so, yeah, I encourage you to do that for your own projects. If you're training on data from the internet, then maybe go out into the real world and take a real image and try that on the model that you trained. So
that would be fun.
Yeah. Maybe you have some ideas already what you want to do. So there's one other thing. Let's see if this is perfect. So this code here, this is a whole long chunk of code. Now we've already trained the model. We've already validated it and tested it. So everything that comes after here is just bonus material. Keep that in mind. You don't have to do this for your own project. But this is a really cool piece of code that shows something called intermediate representations. And let me see if I can sort of explain what it is. So I passed this picture of a dog into the model, and the model said this is a cat, right? So I'm curious, like, what is the model actually looking at here? Like, is it the eyes? Is it the tongue? Is it these cute little teeth up here in front? Like, what's going on? We know what the architecture of the model looks like here, and it's pretty simple. So we have these 16 convolutional filters, and then we have one feed forward neural network with ReLU activation function.
Right.
So it's probably, there might be something going on like in these filters, and we already talked about the feature maps. So there's actually a way to sort of visualize those feature maps as you would expect from Naveed's lecture, and to actually show them. And so here we see 16 little images. Let me see if this will work. Okay, cool. You can sort of see, here, you can sort of see what's going on here, right? So,
Yep.
so we have these 16 little images, which are one for each filter. And yeah, it's just showing the intermediate representations of this dog. And I think this is kind of interesting because I was wondering, like, oh, is the tongue a big deal? It doesn't really seem to be looking a lot at the tongue. It seems to be looking a lot at his sort of the line,
Outline.
yeah,
Yeah.
the line around his furry little face,
Mhm.
and this sort of fur around his his neck and the front of his face. And you can never, when you're looking at these, like, you can never really know exactly what's happening, but it sort of leads me to think that it's just focused a lot on this sort of furry area up here, and it's sort of just getting confused there. It's not it's obviously not seeing the outline of a dog, it's not seeing a tail, it's not seeing it's just looking in, and probably it's detecting, this is sort of me just clearly speculating, probably because it doesn't have the full dog, it's sort of looking at this outline here, and that's what's got it confused. Just me
Yeah.
what I
Maybe
think.
because all of the fur, it's too much.
Yeah, too much.
Yeah.
So so that's just a fun little visualization that you can do, and that's it. This is just a random dog from the data set. So so yeah, that's the project. Do you have any questions about this this notebook here?
Not at the moment, but I'll be looking at the code for a while. And
Yeah.
then I'll let you know.
What about you, Victor?
Yeah, I think there's a lot to learn about this code. I'll have like go ahead and study it.
Sure.
Yeah,
Understand
same.
it.
Yeah. Fortunately, I'd say it's 2/3, 3/4 the same as the last notebook. But yeah, the parts that are not the same, the parts that are different, that's where that's where you're gonna realize, you'll be like, oh, this looks the same, and then you'll see, oh, this one line has so much information packed into it. Like everything we talked about, Naveed talked about for the first half an hour, is just packed into this one line of code now, right? So
Yep.
a lot to understand. And yeah, I've I've just listed like a few different data sets here. There's not, here, let me show that like this. There's not like,
Thank you.
I didn't spend a lot of time looking for images. I figure you should really just find something that's interesting to you. And yeah, I mean, if you're feeling motivated, you can even go outside and take 20 pictures of one thing, 20 pictures of another. It doesn't, you don't need to, the goal for this isn't to make the most accurate model possible. It's just to
Right.
try something out.
Mm-hmm. Yeah, sweet.
Cool. Well, that is it for today.
That was interesting.
Yeah, it's really cool. Just the idea of the built. And yeah, we'll come back on Monday and we'll see what results you both have, and then aside from there, I guess the final week, we can pick one more special topic that we want to learn about. Sound good?
Sounds good.
All right. Thanks, guys.
Thank you. Have a
Thank
good
you.
day.
Nice to
Next
see you
week.
guys.
Bye.
Nice to see you guys.
Bye. Take care.
Bye.